Conservation of energy. It's the same principle as momentum, right? Initial is equal to final, but this time, instead of looking at momentum, we're looking at energy. And we have two different formulas for energy that we're going to be using right now. We have the potential energy, which we say is equal to mgh, g as in gravity on Earth, right? And we have kinetic energy, which we say is 1/2 mv squared. Cool. So in each of these equations, there's a variable that's subject to change. I'm going to erase kinetic energy right now, and I'm going to write potential a little bit bigger so we can see this. Potential energy, which we say is equal to mass times gravity times height. Does mass of an object change? Not really. No, that sort of stays stationary. Does gravity ever change on Earth? No, not really. That stays stationary. So really what we're looking at here is the height, right? The height is our independent variable. So if I draw it out right here, these are different heights of a cliff, all right? The potential energy on the ground is 0 because our height is 0. But if we go up to a height of 1, then we multiply by 1. A height of 3, multiply by 3. A height of 5, multiply by 5. So as our height's changing, the potential energy is really the energy of how high we are. Let's look at kinetic energy. Our kinetic energy is equal to 1/2 mass times velocity squared. This is something that you'll be seeing basically for the rest of your time in physics. 1/2 mv squared. This 1/2 doesn't change, it stays the same. The mass doesn't change, but our velocity does change. So our velocity is the independent variable of our kinetic energy. The kinetic energy really is the measure of our speed energy. So we have a car. It's going this way at 4 meters per second. Or we have a car going at 8 meters per second. Which car has more kinetic energy? Simple, the one with the faster velocity, right? And it's exponential because it's squared by 2, or it's squared. So this goes to 16, that goes to 8. So it's just an exponentially large curve of the kinetic and potential energy. So how do these two relate? Well, what technically is the truth is the mechanical energy of a system in the initial state is equal to the mechanical energy of a system in its final state. Now, we won't really talk about too many other different types of energy, but mechanical energy is basically moving something from one area to the next. Chemical energy would be burning up food to make calories, or using calories as energy, or batteries would be a good example of chemical energy. But mechanical energy is like the motion of an object. So what it says here is that the potential energy is equal to the kinetic energy. The potential energy of whatever object you have is equal to the kinetic energy. So let's go back to our cliff example. Our potential energy right here, PE equals mgh, is going to be equal to the kinetic energy of the ball at the moment, at the instantaneous moment right before it hits the ground and velocity is 0, right? It's equal to 1/2 mv squared. So we can use these back and forth to find out about energy and the different types of energy and different values. So using this equation, right, mgh equals 1/2 mv squared, that's conservation of energy. Cool.